Good evening, good afternoon, and thanks for coming to the talk. We'll be talking about how can we start making MLIR more friendly to programming languages. So first, we're going to start with a brief motivation. Timer. Does the timer works? Does the timer works? Okay. Okay, there you go. Thanks. MLIR has seen a lot of success with the ML compilers. You got Erie, you got OpenXLA, and they have driven a lot of performance. So that has been reflected upstream. So that means that you get, for example, TOSA or MNREF instead of having more traditional things that you would find in a generic programming language. However, now we've seen that we're starting to get more traditional frontends. We have that Flang has been in development for a while, and it's getting closer to production. Like recently, they got renamed from Flang New to Flang. And then on the other side, we also have Flang AR that got recently approved for upstreaming. And basically, what is important here and on the picture is that they hold these representations, CIR and FIR, and they try to lower it to LLVM. So there's like a pretty straightforward path. And in terms of what we need to expect as a community or what we want, is that in the future, we also get other programming languages coming to MLIR, that being Julia, Rust, and many others. And this thing where you have like all of these generic programming languages coming to MLIR can be a burden to downstream compilers because there's not that much support for representing traditional programming languages. So this ends up leading to a lot of work duplication. So for example, you have that many dialects will be implementing the same alloc operation, the same if operation, or even the same load operation, just because they deemed that was necessary for their purposes because their semantic equivalent was not available in upstream MLIR, which in turn leads to also duplicating things like control flow, flattening, and other passes. So the idea is, how can we alleviate this situation? So now we have some limitations about upstream MLIR to be more concrete. So there's like pretty basic ones that reflect that MLIR for a long time has seen a lot of contributions from the ML compiler community. And this means that, for example, things like structs, alloc has, loads, stores, are not really representable in high-level dialects, which means, for example, on the figure, if you have like an struct operation, it's not like you can go like to Mhc or LLVM or SPIRB because there's this high-level representation. Instead, it means that if you want that struct operation, then you gotta decide if you're gonna go to LLVM or Mhc or SPIRB directly, which in the end, this causes many compilers to start recreating these lowerings. And in many cases, these are pretty straightforward. And the other thing that happens in MLIR is that there's no early exit control flow. And in terms of traditional programming languages, you usually get like your breaks, your continues, your go-tos. And the burden of this is that then if you want to have those, you have to re-implement infrastructure for, again, flattening control flow or incrementing the data flow infrastructure to work on these kinds of representations, because if you try to do them right now, they're just not truly supported. Now, we wanted to alleviate some of these situations, so this is like a first step on this process, and this is a proposal on modularizing the LLVM pointer ops. And basically, the main idea in the pointer dialect is that we can extract the pointer operations from LLVM and put them in their own dialect. And in many cases, we can have like this dual representation that acts in a higher level. So for example, in the figure, what we have is that the pointer operations are acting even on tensors, which is something that currently you cannot do if you were working, for example, with LLVM pointers, because LLVM would complain that that is not a type supported by LLVM. So the idea is to also make them target independent so that it can go to Mtg. And this pointer dialect has already gone through the RFC and has begun upstreaming. And in terms of what it does, let's begin like with the lowering paths of how pointer would look. And in this case, what we want is, for example, being able to go to manref to pointer, and then to Mtg or to spherb, which would increase the support for these dialects that in many cases, like they get overlooked because LLVM takes, in some cases, priority. And the biggest difference that we are starting to do here is that these pointer operations are not going to be lowered to the LLVM dialect. Instead, they are going to go straight to LLVM IR and being translated there. So there's not going to be duplication between operations between pointer and LLVM. And one of the nice things is that if we start to abstract these pointer operations into a higher level, we can get many new features. For example, we can introduce restrictions on operations. And in this case, we can have like constant address spaces. So for example, if you try to do a pointer store in a read-only memory space, then you'll get a verification error. And this can also be used to work on things like alias analysis, because if a memory space is constant, then we can assume that it's not going to be conflicting with anyone else. In terms of how it was designed, to make it extensible and to make it friendly to downstream users, we decided to create a attribute interface that encode some of the semantics and abstract them into this interface. So in this interface, you get, for example, things like is valid load, which will return whether a certain type is supported by the address space. And this is how we can get, for example, say, constant address spaces. In terms of the memory model is pretty much inspired by the LLVM in terms that, for example, you have the same weak memory semantics. And one of the nice things is that this leads us to have to clean some of the things upstream. So for example, we can have casting operations from and to memref. And the idea of doing that is that it also allows us to, for example, turn the bear pointer convention into a pass, which stabilizes the ABI right now. Because if you ever use it, the allow bear pointer convention does not work well if you have a static sizes on the memref and dynamic sizes, because it also goes through dialect conversion, and then it becomes tricky. And one of the important things that we need to say, because we need to measure it, is what are the performance impacts of saying we modularize the pointer operations from LLVM. And in terms of performance, we tested out in some synthetic tests, and in most of the cases, we saw that the impact was less than 3%. Also, this can act as a complete replacement of LLVM pointers, of LLVM pointer operations. And in terms, for example, of the implementation, this means that you can just switch from one to another in the beginning and don't notice a difference. So for example, on my implementation of the patch, you have that flank never sees major disruptions on the code. So, and that is also important.
All right. So thanks, Fabian. So Fabian showed you the pointer dialect, which is maybe the first instantiation of a pattern where we extract something from the LLVM dialect to generalize it to work on higher level types. And this is something we can do thanks to types interface or attributes interface. But the same pattern exists on other aspects of the LLVM dialect. What we see in some compilers that we implement, or that at least I'm working on downstream, is that there are a bunch of operation and dialects that are really so close to LLVM semantics that they can be directly translated to LLVM-IR. Like the SCF dialect, if you have just an if or an SCF4, it's pretty straightforward to translate it directly to blocks in LLVM-IR. The arith dialect, when not operating on tensors, is one-to-one to all the LLVM arithmetic operation. And the pointer dialect, only when operating on LLVM types, as well as Fabian just showed you, is something that can be directly translated. And this is pretty important for JIT because of the compile time involved. Like, we save dialect conversions in the process. And so this is something we had to go through downstream, where we started to have a compiler targeting directly the LLVM dialect instead of using the arith dialect, just for the sake of compile time. We were saving dialect conversion. Now, the problem we had was that a lot of canonicalizer and other things only exist on arith dialect. And so now we had to move back. And so we implemented, we added arith in our compiler, but we regressed our compile time. So we had this problem. And so now we are adding direct translation from arith to LLVM to compensate for that. So there is this unfortunate duplication at this point. And so the modularization that we could propose for the LLVM dialect would be to say, like, let's not duplicate operations, but let's reuse as much as possible. So, so we could stop using having even existing an LLVM.add when it's exactly one-to-one to the arith.add for the LLVM types. So something else that we can start doing is that reusing those abstractions for higher level types and start building abstractions that are target independent and retargetable. So the problem with this is that the LLVM dialect is no longer one-to-one mapping to LLVM-IR. It's a collection of dialect that represent the LLVM-IR in MLIR. So that's a trade-off to make, right? It simplifies, like, we don't duplicate documentation, we don't duplicate a bunch of things, but we have to deal with a collection of dialect that collectively represent LLVM-IR in MLIR. And this is basically some of the trade-offs on what we're trying to solve. So yeah, so basically this is what I was saying about arith.add-I and LLVM.add. Over time, arith originally had the loose semantic, in terms of how it was defined, but as people have been starting building production compiler, they wanted better defined semantic, and they wanted to have the control using arith to target all the LLVM semantic. And so we end up by converging de facto the arith dialect with the LLVM dialect in terms of adding all the same flags and all the same semantics. So this is reducing some redundancy. And in terms of compile time impact that I was talking about, we have this translation. We built a proof of concept of and synthetic tests for this translation. And so the conversion to LLVM that we measure here is starting from the arith dialect, having to do the dialect conversion and the translation. So that's going to be the last row. We get a 1.5 speed up basically by translating directly from arith instead of adding this extra dialect conversion that is just one-to-one basically. So there is really real benefits in practice to do that. All right, so beyond this modularization of the dialect, the LLVM dialect, there is like how do we expose those some operation to higher level types and how we abstract ABI and things like that. So there are like things like structure or arrays where those could be fairly simple dialects, don't need a lot of operations, but that could unify the way we manipulate structures and other aggregates types and allow people to inject their own types and inject their lowering and still have access to all of this. So this is just an example of what it could look like. We haven't built those dialects, right? We've just been brainstorming what would be the front-end needs and how we could unify those. And so the question is like, are we going towards a collection of dialects for programming language? How far do we need to go? How far can we build reusable things that are actually useful for the kind of language Fabian was thinking of at the beginning? Like here we show a add scope exit, for example. We show a try catch, so an exception abstraction, for example. And so it's not clear how far we can generalize those kind of things and make them universally useful. And so it's mostly brainstorming at this point and requests for comments from the community and trying to see what are the needs and what could be useful. The one that I know is useful and that many people, even in the last 2 days, have been requesting is this kind of construct where within a loop and within a nested if you want to break out of a loop or continue or return from the enclosing function. This is something that is not legal in MLIR. You can get away with it in your own compiler if you don't reuse too much of upstream components. Like Mojo, for example, rely a lot on those kind of things. But there is no first-class support in MLIR, and that would break the data flow analysis. That would break a bunch of component upstream that tries to understand post-domination properties between operation because we make assumptions about this not being possible. So this is the last bullet here, which is really the impact on analysis, dominance, etc. But there are a bunch of people working on it, so it's coming. We don't have a date for it. We don't have a final design. But hopefully by the next Euro LLVM conference, we should have this implemented. That's really what I expect. So finally, the target ABI abstraction is a pretty big thing. As you know, LLVM is ABI specific, meaning the front ends have to know about the target ABI and has to encode all those decisions before emitting LLVM IR. So in MLIR, it's the same. If you use the LLVM dialect, you have to make all those decisions. And that makes interacting with C a bit complicated. And that's why if you've ever been using memref and try to write a C runtime for memref in MLIR, there's like a complicated ABI that MLIR tries to implement just for the sake of not having to know about the difference between the various targets. And so Clang itself, the front end, encode all the knowledge about the Itanium C++ calling convention for every targets that they support. And there is something to be done here about extracting this from Clang and making it, independent of the Clang C type system and making it available to other front end, including MLIR. And that would allow to build things in MLIR where people could express their type system in terms of the C type system and get for free for x86 or for ARM, whatever, the lowering to LLVM calling conventions and other ABI aspects, layouts and everything. LLVM originally was trying to be an IR that is data layout independent, and that's a goal that was abandoned more than 10 years ago. But in MLIR now we're moving towards building kind of this property, right? An IR where above the LLVM dialect and above the dialect, we should be able to express things in a very ABI independent things. And yeah, so that's the end. We hope that it opens up ideas. We are looking for more ideas that would be needed for programming language in MLIR, so we're looking for more. And thank you for attending.
Questions?
So I have two questions. So for the region-based control flow RFC, would you happen to know what are the main blockers currently? I remember there was a proposal to adopt the RF dialect that was used in Mojo.
So the problem is not a dialect thing, it's really the core of MLIR, right? It's first we have to update longref to allow this, right? Then we have to decide how do you model those new operations, like when you see this continue inside the if, how do you know which operation does the continue map to, right? We need some sort of a label to express that, right? Are we going to support this by adding a new field on the class operation, really the core of MLIR, to build a new edge in this, or are we going to use like the symbol interface, more a name-based things? How do transformation are supposed to update it, right? If you want to unroll this loop, how do you find all the continue there or all the break, those kind of things. So we have to solve some infrastructure questions.
Pinning down the semantics, basically, I suppose. But
yeah.
Parts like, for example, relaxing the rule that each terminator has to be a block terminator, I suppose there are parts that may be less controversial, perhaps.
Yeah.
Right.
Yeah, it's the kind of thing we have to solve. Yeah.
Right. And the second part is in the ideas. So I'm thinking beyond the structures and array. I wonder if the design would make sense would also to be representing the data collections. And I'm specifically thinking of the design from the CGO paper this year, representing data collections in an SSA form, which allows to teach the compilers about a whole variety of data collections like hash tables or maps or trees.
I haven't seen this paper. I don't know if you're familiar with this
CGO
one.
2024 this year.
No, I haven't seen that paper either.
Well,
Right, fair enough, we can follow up.
I definitely look this up. Yeah, thank you for the pointer.
Thank you.
So, at the CF dialect level, I guess you can have these continues and return. I don't know about return, but I guess you want to have this at the SCF level, right? Because the CF level is like is much closer to LLVM.
Sorry, I didn't quite get.
So I mean, at the CF dialect level, could we have all this, the continue, and because that's just like
Yeah, I mean, if
jump from any level to
if you
any
don't have region, you don't have nest, you don't have any nesting, you have a flat CFG.
Yeah.
Then everything is branches.
Yes.
Right?
Yeah.
So there's nothing to add there, I guess.
Yeah.
The problem is only for structured control flow.
But we want this at the SCF level, and so what about the next level? Like at a fine, you can't have this. So I guess that it comes in at this.
It can be, the Clang IR, the Flang IR. I think probably needs those kind of things.
Yeah.
Any kind of programming language where, like Mojo needs this, and so anything that is even above SCF, if they don't use SCF, is this. But yeah, those are for SCF kind of.
Yeah. Okay. Thanks.
Other questions? Well, let's thank the speakers again.